Renaissance Europe marked a profound turning point in history, a period when the rigid structures of medieval thought began to crumble under the weight of curiosity and innovation. In this era, art, science, and literature emerged in a triumphant symphony of exploration, setting the stage for a revolution in every sphere of life. The old world, with its strict hierarchies and dogmatic beliefs, was given way to a new age where inquiry and human ingenuity reigned supreme. During this period, Europe became a fertile ground for intellectual growth. Cities like Florence, Venice, and Paris buzzed with lively debates, and scholars, artists, and philosophers gathered in coffeehouses and grand halls alike, discussing ideas that challenged the accepted wisdom of their predecessors. The invention of the printing press played a crucial role, disseminating groundbreaking ideas far and wide and allowing the collective mind of society to expand in unprecedented ways. These new ideas questioned long-standing beliefs about the cosmos, the divine, and the natural order of things. This era witnessed a daring shift, a move away from simply accepting inherited knowledge to actively seeking out new explanations through observation, experimentation, and critical thinking. It wasn't just about art or literature. The Renaissance fostered a scientific curiosity that laid the groundwork for modern astronomy. Scholars began to peel back the layers of ancient texts and challenge the geocentric view that had long held sway over European thought. The idea that Earth was the universe's pivot was starting to seem less certain under the modern lens of rational inquiry. In this environment of intellectual liberation, the cosmic order was being reimagined. Renewed faith in human reasoning and empirical evidence made it possible for bold thinkers to propose radical new theories, the very ideas that would later set the stage for transformative astronomical discoveries. As Europe awoke to a world of possibilities, every investigation, every artistic flourish, and every spirited debate contributed to a growing body of knowledge that sought to understand the workings of the universe in all of its complexity. This vibrant awakening created the perfect context for future pioneers in astronomy. It was the fertile soil in which revolutionary figures like Copernicus and Kepler would eventually plant the seeds of new cosmic vision, a vision that would forever change the way humanity perceives its place among the stars. For centuries, the cosmos was viewed through a lens that positioned Earth at the center, a neatly ordered, almost poetic arrangement that appealed to both reason and divine aesthetics. The prevailing geocentric model, inherited from ancient Greek philosophy and later cemented by medieval scholars, portrayed the universe as a series of concentric spheres with Earth at its core. Every star, planet, and celestial body was thought to revolve in perfect circles around our world, a model that resonated with the idea of cosmic perfection. Yet, even as this model held sway, small but nagging inconsistencies began to emerge. Astronomers noted that the graceful paths of the stars did not always conform to the elegant loops and circles that tradition demanded. The puzzling retrograde motion of planets, wherein they appeared to reverse direction for a time, was one such mystery. These observational quirks posed a fundamental challenge. How could a universe designed with divine perfection exhibit such irregularity? This question laid the groundwork for a slow but inevitable paradigm shift. As the Renaissance unfurled its vibrant tapestry across Europe, new tools and techniques in measurement and observation began to take root. Scholars started to rely more on empirical evidence rather than solely on ancient texts or religious dogma. Instruments, though still rudimentary, provided more precise data, and the results began to strain the limits of the geocentric explanation. There was a growing realization that the celestial sphere might not be as perfect as once thought, that perhaps the universe was not a static stage but a dynamic arena governed by natural laws. This awakening prompted scholars to delve deeper into understanding the true nature of planetary motion. The classical idea of perfect circular orbits and aesthetic ideal of the heavens was gradually being replaced by a more complex reality. The growing emphasis on mathematical analysis and systematic observation encouraged astronomers to look beyond tradition. They began to see that the heavens might be governed not by ornate geometries or fixed spheres, but by more elusive and intricate patterns that called for a radical rethinking of cosmic order. This shift was not merely a technical correction, it was a profound transformation in how humanity perceived the universe. The rigid framework of ancient models started to give way to a vision of a cosmos that was both more chaotic and more fascinating than previously imagined. A universe that could be deciphered through careful observation and rational thought, rather than one that rested solely on philosophical and theological dictates. Moreover, this emerging paradigm invited an interdisciplinary approach where mathematics, philosophy, and astronomy converged. Observers began charting planetary motions with renewed diligence, drawing on the power of numbers and geometric reasoning to explain what the naked eye could see. This collaborative spirit between theoretical speculation and practical measurement set the stage for later breakthroughs that would further demystify the cosmos. In essence, this period marked a pivotal moment, when the old, static view of the universe began to crumble under the weight of fresh observations and more inquisitive spirit. The gradual dismantling of the geocentric model birthed a new era in which the cosmos was seen as an ever-changing expanse, a realm of motion and mystery waiting to be understood. This transformative shift in perspective not only redefined our understanding of the heavens, but also laid the crucial intellectual foundation for the revolutionary insights of future astronomers. Amid the vibrant intellectual stirrings of Renaissance Europe, one figure stood poised to reimagine the cosmos in a way that transcended the ancient models: Nicolaus Copernicus. Born into a world governed by tradition and the unwavering certainty of geocentric thought, Copernicus nurtured curiosity that defied the prevailing norms of his time. Rather than clinging to the long-revered notion that the Earth was the immovable center of celestial order, he began to see the universe through a radically different lens. His journey was neither sudden nor facile. It was the product of patience, meticulous research, and the willingness to challenge centuries of established wisdom. In an era where scholarly life was intertwined with the rigid directives of the Church and Aristotelian philosophy, Copernicus's ideas emerged like a quiet yet persistent force. As he immersed himself in the study of mathematics, astronomy, and ancient texts, he encountered hints of earlier heliocentrism, ideas that had flickered in history but never received the clarity they deserved. With careful observation and analytical mindset, Copernicus pieced together astronomical puzzles that had long baffled his predecessors. His revolutionary insight was to reposition the Sun, not the Earth, at the center of the known universe. This audacious idea, detailed in his seminal work De Revolutionibus Orbium Coelestium, was more than a mere adjustment of celestial coordinates. It was a profound paradigm shift. Copernicus proposed that Earth, along with its fellow planets, gracefully orbited the Sun in a harmonious dance. By doing so, he provided a simpler and more unified explanation for the irregularities noted in planetary motion, such as the perplexing retrograde motion that had confounded scholars for generations. His model suggested that what appeared as aberrant movements were in fact the natural consequences of our planet's own shifting position relative to its luminous center. The implications of Copernicus's theory extended far beyond astronomy. By decentering Earth from the cosmic stage, his work questioned humanity's assumed centrality in the universe and invited a more humble yet expansive view of nature's orders. This perspective challenged not only scientific dogmas, but also philosophical and theological constructs that had defined medieval life. As Copernicus meticulously laid out his observations and mathematical calculations, he offered a vision of a universe governed by consistent principles, a vision that would eventually pave the way for later giants like Kepler and Galileo. Throughout his life, Copernicus exhibited a blend of caution and conviction. A dedicated canon at Fromborg Cathedral, he balanced his ecclesiastical duties with virtuosic scholarship, aware that his ideas invited both intrigue and potential ire. His commitment to empirical evidence and rational inquiry carved out a new method of scientific exploration, one that relied on observation and calculation rather than unquestioned tradition. Even as his ideas ignited controversy, particularly among conservative scholars and religious authorities, they gradually ignited debate that would fuel centuries of astronomical advancement. Copernicus's intellectual legacy is woven into the very fabric of modern science. His willingness to challenge the established order not only redefined the movement of heavenly bodies, but also set in motion a chain reaction of discoveries. Through his clear yet bold questioning of old assumptions, Copernicus transformed how humanity would come to understand its place in the cosmos, a transformation that continues to inspire thinkers and explorers alike. The introduction of heliocentric model marked a radical turning point in our understanding of celestial mechanics. As Copernicus's theory began to take shape, the very foundations of astronomical thought were shaken. The heliocentric universe did not merely rearrange the positions of cosmic bodies, it provided an entirely new lens through which to understand the workings of the heavens, offering clarity and simplicity where confusion had reigned for centuries. At the core of his new perspective was a straightforward yet profound observation. The Sun, rather than the Earth, occupied the central stage. This repositioning brought with it a host of explanations and phenomena that had long mystified astronomers. For example, the erratic retrograde motion of planets, the seeming backwards movement observed from Earth, became a natural consequence of our own planet's orbital dance around the Sun. Rather than resorting to complex systems of epicycles and difference to explain these irregularities, the heliocentric model provided an elegant solution that resonated not only with mathematical logic but also with everyday observation. The shift to a sun-centered cosmos invited scholars to re-examine every known detail about planetary motion. By placing the Sun at the centerpiece, astronomers could trace the paths of celestial bodies with newfound simplicity. Every orbit, every shift in brightness, and every apparent collision of orbits across the night sky found a more coherent explanation. This clarity encouraged a move away from relying solely on ancient texts and philosophical traditions towards a dynamic model built on empirical observation and critical analysis. As scholars began to test and validate this model, the heliocentric view quickly emerged from the realm of abstract speculation into the core of scientific discourse. Furthermore, unveiling this new celestial perspective helped break the psychological and intellectual chains that had long tethered humanity to a geocentric narrative. The model not only challenged the scientific ideas of the day, but also the deeply ingrained belief in humankind's centrality in the universe. With the Sun as the axis of our planetary system, a new humility and curiosity were instilled among scholars and the broader public alike. The cosmos ceased to be an orderly stage with Earth as its crown jewel, and became instead a vast, interconnected system where every planet played a part in a grand cosmic ballet. Importantly, the heliocentric universe did not stand in isolation. It created the fertile ground from which later scientific advancements would grow. The model's emphasis on observation and mathematical consistency paved the way for subsequent astronomers. It provided a framework that allowed thinkers like Johannes Kepler to delve deeper into the precise mechanics of orbital motion, ultimately uncovering the elliptical nature of planetary paths and the laws that govern them. This evolutionary step transformed our view of the universe from a static, almost mythic portrait into a dynamic, mathematically governed system of motion. Ultimately, unveiling the heliocentric universe was about more than just revising diagrams in the sky. It represented the triumph of reason, observation, and an unwavering commitment to understanding the natural world. The clarity it brought to the chaotic dance of the heavens challenged all paradigms and inspired generations of thinkers to continue questioning and exploring. With each new observation, the narrative of the cosmos grew richer and more engaging, reflecting a universe that was less a rigid structure of divine perfection and more a vibrant, ever-evolving tapestry of cosmic wonder. The cosmos, as re-envisioned by Copernicus, was a stage primed for further inquiry, but it still held mysteries that beckoned for deeper interpretation. Enter Johannes Kepler, whose genius transformed the hesitant chords of heliocentric model into a full-blown symphony of cosmic harmony. Kepler's work was less about rigid geometry and more about deciphering the natural rhythms of the universe, a pursuit that can be described as listening to the music of the spheres. Kepler inherited a celestial puzzle that had begun to hint at hidden complexities. With the meticulous observations of Tycho Brahe as his guide, Kepler set out to chart the true paths that planets traced as they journeyed around the Sun. The prevailing notion of perfect, circular orbits gradually gave way to a startling realization. The planets moved not in unyielding circles, but in elegant, elongated ellipses. This discovery, encapsulated in his first law of planetary motion, was a pivotal moment. It revealed that the heavens were not governed by an idealized static order, but by a dynamic and measurable harmony. For Kepler, the idea of elliptical orbits was akin to uncovering a cosmic melody that had always been there, hidden behind the illusion of perfection. He proposed that each planet's path is an ellipse, with the Sun at one focus. A concept that not only explained observed phenomena like retrograde motion more simply, but also introduced a new level of mathematical precision to astronomy. His insight was a brilliant blend of observation and intuition, a process that mirrored the rigorous training of a musician attuned to every nuanced note in a complex orchestration. As Kepler delved deeper, he uncovered further layers of cosmic rhythm. His second law, which states that a planet sweeps out equal areas in equal times, provided a glimpse into the inherent flows of celestial movement. This law illustrated how planetary speeds vary. As planets approach the Sun, they move faster. As they drift away, they slow down. This variation wasn't random. It was nature's way of keeping a perfect balance. In essence, Kepler was decoding the time signatures of the universe, revealing that the cosmos obeyed principles of rhythm and balance similar to those found in music. Yet perhaps his most profound contribution was his third law, forged from painstaking calculations that linked the orbital periods of the planets to their distances from the Sun. This harmonic law showed that the square of a planet's orbital period is directly proportional to the cube of its semi-major axis. Such a relationship offered a mathematical elegance to planetary motions that resonated deeply with the ancient idea of cosmic music, a universe where every celestial body played its part in a grand orchestrated performance. Kepler's journey was not just one of scientific discovery, it was a quest to understand nature's secret score. His willingness to let empirical data guide his intuition transformed our understanding of the cosmos. The brilliance of his work laid the groundwork for future luminaries like Newton, who would further unravel the gravitational forces. In the tapestry of scientific revolution, Kepler's legacy is that of a composer who listened carefully to the whispers of the universe, transcribed its hidden harmonies, and encouraged humanity to appreciate the cosmic dance in all its intricate beauty. His laws continue to echo in modern astronomy, a timeless reminder that the universe, much like a symphony, is a masterpiece of order, rhythm, and wonder. Kepler's revelation of his three laws signified more than a series of scientific statements. It was the unveiling of an intricate dance, a cosmic choreography that transformed the way humanity perceived celestial motion. Building on the heliocentric frame introduced by Copernicus, Kepler's law provided the mathematical language to describe how planets truly move and interact in a dynamic universe. Kepler's first law, the elliptical orbit. The first law shattered the long-held belief in perfect circles. Kepler proposed that planets move in ellipses, not circles, with the Sun occupying the center. This elegant adjustment meant that the paths of planets were elongated curves, a departure from the circular orbits that had seemed a divine mandate for centuries. The elliptical shape not only aligned more closely with the detailed astronomical observations, but also infused the cosmos with a realism that the idealized circles simply could not offer. Through his careful analysis of Tycho Brahe's meticulous records, Kepler demonstrated that these elliptical orbits provided a far more precise prediction of planetary positions, a vital clue that the universe was governed not by abstract perfection, but by natural laws accessible to human understanding. Kepler's second law, equal areas in equal times. If the first law set the stage, the second law revealed the rhythm of the celestial dance. According to this principle, a line drawn from a planet to the Sun sweeps out equal areas in equal intervals of time. This law imparts a sense of balance and timing to planetary motion. In practical terms, it means that planets move faster when they are closer to the Sun and slower when they are further away. This speed is not arbitrary. It's a precise mechanism that ensures the conservation of angular momentum. Through this observation, Kepler provided an intuitive understanding of the forces at play, showing that the energy and timing woven into the fabric of space were in perfect harmony with nature's design. Kepler's third law, the harmonious relationship of distances and periods. Perhaps the most mathematically striking of his insights, the third law establishes a clear relationship between the orbital period of a planet and its distance from the Sun. In its simplest form, the square of a planet's orbital period is directly proportional to the cube of the lengths of its semi-major axis. This law created a predictable framework, linking the time a planet takes to orbit the Sun with the size of its orbit. The profound elegance of this relationship is that it applies uniformly across all planets, regardless of their individual characteristics. This discovery not only highlighted the inherent order within the cosmos, but also provided a powerful tool for predicting planetary positions and understanding the structure of our solar system. Together, these laws transformed what had once seemed like an erratic, inexplicable motions into a coherent dance, a fluid interplay of speed, distance, and geometric precision. Kepler's law allowed astronomers to move beyond simple observation. They provided the rigorous mathematical foundation needed to model the motions of planets. In essence, what was once a celestial jigsaw puzzle now emerged as a harmonious symphony that united empirical observation with elegant mathematical truths. This new understanding of planetary motion not only enhanced the predictive capabilities of future astronomers, but also instilled a sense of wonder about the cosmic order. Kepler's meticulous work served as a bridge from the observational insights of the Renaissance to the advanced gravitational theories of Newton and beyond. His laws are a timeless reminder that the universe, with all of its complexity, follows the rules that can be expressed as a graceful dance, a dance that continues to inspire scientists and astronomers alike. In the early decades of the 17th century, Galileo Galilei emerged as a pioneering force with a passion for unraveling the hidden details of the cosmos. Driven by his curiosity and armed with an innovative spirit, Galileo transformed a modest optical instrument into a powerful telescope that would forever alter humanity's window to the heavens. Galileo's enhancements to the telescope allowed him to pierce the veil of the naked eye. When he turned his instrument skyward, the familiar celestial canvas revealed a startlingly different picture. The moon, long thought to be a perfect, unblemished orb, appeared rugged and scarred with mountains, valleys and craters, a dynamic landscape rather than an immutable sphere. This observation not only upended the Aristotelian idea of celestial perfection, but also heralded a transformative period in the scientific approach toward astronomy. Perhaps his most revolutionary discovery came when he observed Jupiter. Instead of a solitary, majestic planet, Galileo found 4 bright objects, later known as the Galilean moons, orbiting around Jupiter. This was a profound demonstration that not all celestial bodies orbited the Earth, providing potent evidence in favor of the heliocentric model advanced by Copernicus and refined by Kepler. His detailed notes and precise sketches captured the motions of these moons, rendering the invisible dynamics of the cosmos accessible to a skeptical audience and challenging the entrenched geocentric view. Yet Galileo's ingenuity did not stop there. His observations of the phases of Venus further undermined the geocentric paradigm by showing that Venus exhibited a full sequence of phases similar to the moon. This could only be reconciled with the model of a sun-centered system. Additionally, Galileo's study of the Milky Way revealed that what had been perceived as a continuous band of light was actually a dense swarm of innumerable stars. This discovery expanded the known boundaries of the universe and served as a call to re-examine the fabric of the cosmos. Beyond these groundbreaking discoveries, Galileo's methodical approach was as transformative as his observations. He championed rigorous empirical inquiry, meticulously recording data and repeating experiments to ensure reliability. In doing so, he laid down one of the earliest foundations of the modern scientific method. His willingness to challenge established dogma through observation and evidence fundamentally redefined how questions about nature were to be answered. Galileo's telescopic triumph was not merely a leap in technology, it was a bold expedition into the unseen. With each new observation, he invited the world to view the universe not as a static tapestry of divine perfection, but as a vibrant, ever-changing arena of natural phenomena. His work opened the doors for future astronomers and scientists who would continue to peel back the layers of cosmic mystery, cementing his role as a true pioneer of modern astronomy. While Galileo's telescopic revelations lit up the night sky with newfound wonders, they also cast a long, challenging shadow on his personal journey. A journey marked by confrontation, conflict, and a steadfast commitment to the truth. Galileo's discoveries, revolutionary as they were, thrust him into a bitter clash with powerful authorities who clung to traditional geocentric doctrines. As Galileo's findings began to gain traction, they soon came under fire from the religious and political establishments of his day. His insistence that the heavens obeyed empirical evidence rather than rigid interpretation of ancient texts brought him head-to-head with the prevailing forces of the Church. In 1633, Galileo found himself on trial for heresy, a trial that would become one of the most notorious episodes in the history of science. Despite being forced to recant his heliocentric views under pressure, his ideas had already set in motion a shift in human thought that could not be easily reversed. Galileo's struggle was not only a fight for his personal freedom, it was emblematic of a larger battle for intellectual liberation. Faced with the might of institutional dogma, he championed an approach rooted in personal observation, rigorous experimentation, and a willingness to question assumptions. Even under house arrest in the later years of his life, Galileo's writings continued to inspire quiet revolutions among scholars. His works, written with careful reasoning and poetic descriptions of the cosmos, resonated deeply with those seeking a more truthful connection with nature. The implications of Galileo's defiance extended far beyond his own lifetime. His trial and subsequent silence did little to stifle his legacy. Instead, they transformed him into a symbol of intellectual courage, a reminder that the pursuit of knowledge often requires a personal sacrifice. His experiences galvanized future generations of scientists who summoned the strength of empirical evidence, and the methods he had helped refine would eventually break free from the chains of dogmatic constraints. Galileo's influence is palpable even today. Modern astronomy, physics, and the broader scientific community owe a great debt to his relentless questioning and his commitment to uncovering the truth. His life story, a thrilling mix of triumphs, trials, and unwavering dedication, continues to inspire not only scientists, but anyone who dares to look beyond what is immediately visible, to question the status quo, and to seek a deeper understanding of the universe. Galileo's battle for truth remains an enduring legacy. His courage to confront established norms in pursuit of natural laws has become a rallying cry for free inquiry, reminding us that sometimes the most profound breakthroughs come at a personal cost. His life and work continue to light a path of discovery, encouraging us to look, to question, and ultimately to embrace the transformative power of genuine observation. The transformative ideas of Renaissance astronomers ignited a revolution that forever changed the humanity's view of the cosmos. The groundbreaking work of Copernicus and Kepler not only redefined celestial mechanics but also reshaped our collective understanding of our place in the universe. Their contributions continue to ripple through time, inspiring generations of thinkers and explorers and laying the intellectual groundwork from which modern astronomy emerged. Copernicus's bold assertion that the Sun, not the Earth, laid at the center of cosmic system challenged centuries of established thought. His heliocentric model was the spark that lit the fire of inquiry during a period when questioning tradition was a daring act. This model did more than rearrange planetary positions. It signified a seismic shift toward empirical investigation and reasoned debate. It urged humanity to discard comforting certainties for a more complex yet profoundly realistic portrayal of the universe. By questioning the status quo, Copernicus instilled an enduring lesson. The pursuit of truth is best served by challenging established paradigms when evidence calls for it. Building on this audacious foundation, Johannes Kepler transformed the abstract idea of a sun-centered universe into a dynamic, mathematically coherent system. His insightful observations revealed that the orbits of planets were not perfect circles, but elegant ellipses, each expressing a harmonious balance between motion and distance. Kepler's three laws of planetary motion provided a tangible framework that explained previously puzzling phenomena, such as retrograde motion, by tying observed behavior to the geometry of the heavens. By doing so, he not only validated Copernican theory through rigorous analysis, but also improved it with a predictive power that was entirely novel in astronomy. The combined legacy of Copernicus and Kepler ignited further breakthroughs in scientific thought. Their willingness to innovate beyond conventional boundaries paved the way for later pioneers like Galileo Galilei, who used new instruments, most notably the telescope, to gather additional evidence in support of the heliocentric model. Even Sir Isaac Newton, whose laws of gravitational force united terrestrial mechanics with celestial motion, built upon the empirical and mathematical foundations established during the Renaissance. This intellectual continuum illustrates how the evolving understanding of the heavens was the result of a collaborative journey, a finding nurtured by successive minds, each expanding upon the revelations of those who came before. Beyond the realm of science, the legacy of the Renaissance Revolution influenced philosophy, culture, and the very way human beings relate to the universe. The heliocentric model diminished the notion of human centrality, encouraging a humbler and more inquisitive perspective. It opened our eyes to the grandeur of a cosmos governed by natural laws instead of a divine whim, thus sowing the seeds for modern secular scientific inquiry. The shift in perspective from a universe centered around humanity to one where Earth is one of many celestial players continues to influence contemporary discussion at the intersection of science and philosophy. Today, our modern telescopes, space probes, and astronomical observatories all echo with the principles first articulated over 500 years ago. As we chart distant galaxies or study the intricate dance of exoplanets, we are reminded that our understanding of the cosmos rests on the shoulders of Renaissance giants. Their resolve to pursue observation, embrace mathematics, and challenge dogmatic boundaries has given us powerful tools to explore the universe. The legacy of the Renaissance Revolution is not merely measured in scientific laws and astronomical models. It is an enduring call to curiosity and courage. It inspires us to keep probing the unknown, to refine our theories, and above all, to remain open to new vistas of discovery. A legacy that even today lights our path to the stars. The journey through the Renaissance Europe reveals a transformative era when human curiosity broke free from medieval constraints, igniting a revolution in our understanding of the universe. This period was a testament to the power of questioning established norms, a spirit that drove visionaries like Copernicus, Kepler and Galileo to redefine how we perceive the cosmos. Copernicus dared to uproot the geocentric view that had dominated for centuries, positioning the Sun and not the Earth as the center of our celestial system. His heliocentric model, documented with clarity and conviction, not only simplified complex astronomical patterns, but also set in motion a cascade of inquiry that challenged the doctrines of his time. This bold reimagining laid the foundation for a new era, one in which empirical evidence and mathematical reasoning became the tools for unlocking cosmic mysteries. Building upon Copernicus's groundbreaking ideas, Johannes Kepler transformed the conceptual framework of the heliocentric model into a dynamic, measurable system. By revealing that planetary orbits are elliptical and governed by precise laws, Kepler not only resolved long-standing anomalies, but also showcased the inherent harmony of the universe. His laws bridged the gap between raw observation and mathematical elegance, ultimately providing a blueprint that would inspire future discoveries. Galileo's telescopic adventures then expanded the horizons of the cosmic narrative. With his innovative instrument, he unveiled previously unseen details and the multitude of stars in the Milky Way. Galileo's relentless pursuit of truth, despite the fierce opposition he faced, demonstrated the essential role of technology in advancing scientific thought and cemented the importance of empirical inquiry. Today, the legacy of the Renaissance pioneers continues to illuminate our path. Their combined efforts serve as a stirring reminder that the quest for knowledge is an ever-evolving journey, a dance between observation, mathematics, and boundless imagination. In embracing this legacy, we not only honor the trailblazers of the past, but also empower ourselves to challenge the unknown, continually pushing the frontiers of discovery in our cosmic dance. Thank you for watching. Keep looking up.